Okay, so for today, before we resume our last part, I think I'm going to recap a bit what we have learned yesterday. Well, basically, yesterday we have gone through a few things related on intermetallic compounds. So the definition of intermetallic compounds. So basically, intermediate compound, it means that the intermediate that forms, the intermediate phases that forms during the formation or the solid formation, and because of there's a limit of solid solubility, the second phase of intermediate can also present, which actually can be known as intermetallic compound, right? So intermetallic compound have a different crystal structure. It has a different properties as compared to the other types of solid that it may form towards the end. An intermetallic compound can be easily identified. Okay? If you look at any phase diagram that shows a vertical line, any vertical line actually indicating that there's a formation of intermediates. So that is why you didn't see any regions, any like contour, any area that represents one specific phase. But for intermediate, normally just a vertical line, straight vertical line. And other terms that is used to identify intermetallic compound is congruent. Okay, so I hope this one you actually put it in your mind. And yesterday also we have looked through the other types of phase diagram, which is iron carbon phase diagram or cast iron phase diagram. So in cast iron phase diagram, we have a multiple reaction that may occur. First one is basically on eutectic reaction. So we know that from eutectic reaction, we have a liquid that when it solidifies, it forms another two solids. In this case, if we are referring to cast iron phase diagram, the other two solids that it may form is actually gamma austenite and also Fe3C cementite. Apart from that, okay, the essence of cast iron phase diagram is also on eutectoid reaction. So eutectoid reaction forms below than eutectic temperature. So that is why over here you will see that there's also another vertical horizontal line at the lower temperature. The definition of eutectic is basically when you have a solid, okay, a solid that when it further solidifies, it forms another two solid. So in this case, if we are referring to cast iron phase diagram, the solid that may form is actually the solid that initially form is gamma austenite, and then after that it will further solidify to form ferrite and also cementite. And apart from that, I guess another small reaction that also occur is known to be peritectic. So peritectic is the reaction where you have a mixture of solid and liquid that when it's further solidified, it forms one solid. So in this case, we have delta plus with liquid that forms gamma or austenite. Okay, so this is actually the uh, reaction for peritectic process or system. And other than that, we have, I think, tried to digest this phase diagram. Some terms and some, I think, phase is actually related to a specific composition. For example, perlite. So perlite is actually a phase that forms at eutectoid composition, okay, at 0.77. We also have the diborate, okay, that forms at eutectic composition of cast iron, 4.3%. Okay, and I think other than that, we also have cementite that normally forms at around 6.7% of carbon. Okay, um, talking about the iron carbon phase diagram, we also cannot run away with the how to say the microstructure. I think yesterday I forgot to touch a bit on the microstructure at eutectoid range. So over here, if you have like one point that is located at gamma austenite, then you have a formation of polycrystalline gamma. And if the solid or the alloys actually forms at the lower, I think just slightly below than eutectoid temperature, then you'll see that it forms a lamellar structure. Okay. We also have looked through hypoeutectoid and hypereutectoid. So hypoeutectoid actually occurs in the range of 0.0022 to 0.77. Okay, and the microstructure of alloys in this region possible at higher temperature, gamma austenite, polycrystalline gamma, and then you will see that uh, going down, there's formation of I think alpha grains, ferrite grains at the phase boundaries. And when it further goes down, it will actually forms a bigger structure. It combines with each other to form pro-eutectoid alpha. And finally, when it actually reach at alpha plus cementite range or region, then it will form a microstructure that have a background of lamellar structure with pro-eutectoid alpha branch. So similar for hypereutectoid, okay. Hypereutectoid range exists in between 0.77 to 2.3, around 2.3 until here, okay. And then you'll see that the possible microstructure that forms is if you have at higher temperature gamma austenite, polycrystalline gamma, and then after that going down, we start to see a formation of cementite grains at the phase boundary, and when it further goes down, it will combine to form pro-eutectoid cementite, and finally, when it reach in the region of alpha plus cementite, then the microstructure will be a background of lamellar structure with a pro-eutectoid branch. So we have also looked through these examples yesterday. So I guess maybe I'm not going to go into further detail of this. And we also have discussed slightly on the eutectic, eutectoid, and also peritectic reaction that is actually related in the cast iron phase diagram. And before we end yesterday, we have also looked into some other possible systems in phase diagram, which also related to monotectic, peritectic, peritectoid. Okay, so in order how to determine the reaction, as I said, the first thing that you need to remember is that anything that forms a horizontal line in the phase diagram, that actually indicate some reaction. So for eutectic, it's very simple. You see a horizontal line, and then after that, you see the phase boundary between the liquidus and solidus, V shape. If it is actually located on the top of the horizontal line, then the reactant is actually on top and the product will be on the bottom. So in this case, the reaction will be liquid, double head arrow forms alpha plus beta. This normally we have seen a lot in lead tin phase diagram and also in cast iron phase diagram. For eutectoid reaction, similar things. Okay, as in eutectic, you see horizontal line, and then after that, the phase boundaries located on top. So obviously, the reactant will be located on top, which in this case it will be gamma, and gamma itself is actually a solid. Okay, and when it solidifies, it forms another two solid. Okay? So in this case, it forms. If we are referring to this one, the reaction will be gamma double head arrow alpha plus beta. If we are referring to cast iron phase diagram, then the reaction will be gamma plus double head arrow forms alpha plus with cementite. Monotectic, meanwhile, is actually where you have this so-called miscible gap. So miscible gap, which we cannot identify the region, because if you see just beside the phase boundaries, it is actually liquid 1 and liquid 2. So this we are not sure. It's a combination of liquid 1 and liquid 2. So we call it as a miscible gap. So in this case, if we are going to read the phase diagram, it is actually showing you that the lower okay, is actually the reactant and the side is actually the product. This shouldn't be alpha, this should be beta. So that is why later on you will see that the reaction will be alpha plus liquid that will equals to beta. Okay, peritectic, as I said, still horizontal line, but in this case now the phase boundaries is located at the bottom. Of course, what you are going to see is that this will be the reactant and this will be the product. So the reaction that you will see is that alpha plus liquid will forms beta. Okay, almost similar with monotactic. It's just that for monotactic you have this miscible gap, and there's also peritectoid reaction. So peritectoid reaction, where you have two solids. When it solidifies, it forms one solid. So this horizontal line, and you see the phase boundaries located on the bottom. So this still your reactant, and this be your product. Okay, all right. So for a more complicated reactions over here, maybe I don't know. Maybe some of you can identify what would be the reaction apart from the two reactions that have been located here. Maybe I can just ask anyone. Saya nak tanya Amir Mustaqim. Amir Mustaqim ada ke? Amir, ada ke?
Ya, ada saya ada Doktor.
Okay, alright. So Amir, so if you look to this phase diagram, copper zinc phase diagram, you will see that there's a multiple reaction that may occur, and there's a formation of few other things, okay, over here. So if I ask you, how can you actually conclude apa yang Amir boleh nampak daripada phase diagram ni? Apa jenis-jenis reaction yang Amir rasa Amir boleh nampak? From what we have learned lah. I think I've highlighted peritectic and also eutectoid transformation, but there's also another things that maybe could be related with what you have learned just now. Ada ke? Ada yang lain ke? Rasa-rasa?
Sorry, Doctor, I cannot answer the question.
Okay, it's okay. Alright. So first over here we identify peritectic because you see first thing we observe horizontal line at around maybe before or below than 700 degrees C. Okay, so dia punya phase boundaries dia kat bawah, kita nampak kat bawah. I think I should change to other color, maybe purple lah. Okay, so kita nampak dia kat bawah. Alright. So the things will be on top is actually gamma plus liquid, and at the bottom bawah ni apa dia punya produk dia adalah delta. So this is the best example for peritectic lah. So we know that for peritectic, okay, it is actually solid plus with liquid that forms another solid lah. Okay, so ini adalah untuk peritectic. Over here we see eutectoid. Dia cakap eutectoid sebab we still observe a horizontal line, and then we have a phase boundary here. Okay, located on top. So atas dia apa? Kalau saya tanya Amir, atas dia apa Amir?
Dia
Atas dia apa? Dia punya reaktan dia apa agak kat sini?
gamma plus liquid.
Dah ada tulis dah tu. Okay. Delta kita nampak dekat atas ni sebenarnya dia ada solid satu solid which is delta. Okay. So this will be the reactant, and the product kita tengok kat bawah. Bawah nampak yang ni. So delta forms gamma plus with epsilon lah. Okay. So ini sebenarnya adalah merujuk kepada eutectoid reaction, because for eutectoid reaction we know that one solid Okay. When it solidifies, it forms another two solid. So delta, gamma, and epsilon is a solid. Kalau dia liquid, dia tulis L. Kalau dia selain daripada huruf L ni, dia adalah solid lah. Okay. So this actually eutectoid. So other than that, we also notice that there's one horizontal line over here. Okay. Alright. So kita nampak dia punya phase boundary dekat bawah. Okay. So top, dekat atas dia apa? Ini saya nak tanya someone else. How about Crystal? Crystal Chong. Crystal, are you there?
Yes, doctor.
Okay, so Crystal, just want to ask you, what will be the reactant in this case? The other horizontal line that you identified just now.
Delta plus L.
Delta plus S, okay, all right. So delta plus L, so this will be the reactant. And what will be the product?
Epsilon.
Epsilon. So for this one, what kinds of reaction that you think could be related?
Peritectic.
Peritectic, yes. Peritectic. So why do you think that it will be peritectic? How did you indicate?
Because
Mhm.
the reactant is solid plus liquid and form a solid.
Okay, yes, that is actually good lah. As similar as what we have explained earlier. So you have a mixture of solid plus liquid, that when it solidifies, it forms another solid. So it means that in the phase diagram, it is possible that the reaction occurs multiple times, even though you have one peritectic at around 700 something. There's also possibility that peritectic could also forms in other things. So similar for other reaction, you can see a multiple reaction of eutectic, eutectoid, and whatsoever. Okay, so thank you, Crystal. Okay, so any other things that you can see from this phase diagram? Anything that you think you can discuss? Let me ask siapa ni? Izzat Nazri. Izzat ada Izzat?
Ada.
Okay, Izzat. Apa lagi yang kita boleh nampak daripada phase diagram ni? Anything that I miss out? Apart from the reaction.
Liquid.
Liquid?
uh,
Okay, tembak je ni. Okay, tak apa. Okay. How about others? Siapa ni? Muhammad Syami. Muhammad Syami ada Muhammad Syami?
Ada.
Okay, so Syami boleh nampak apa lagi dekat dalam phase diagram ni? Selain daripada reaction yang tadi saya dah beritahu. Apa lagi?
Reaction. Monotektik ke?
Monotektik kat mana tu?
Oh, tak ada.
Kat mana tu?
Dekat boundary. Oh, tak ada.
Ha? Tak ada sebab kita nampak yang horizontal line semua kita dah discuss lah. Semua. Kalau kata nampak monotektik tu kat mana? Kok saya tak nampak lah.
Kayak ada.
Tak pasti
Tak pasti
Okay. Tak apa Syami. Terima kasih kerana mencuba. Okay. Alright. Maybe last person lah I will ask. Siapa ni? Syamimi Jailani. Syamimi ada Syamimi? Syamimi tak ada. Okay. Siti Zulaifa. Siti Zulaifa ada tak? Pun tak ada. Okay. So, the other things that maybe we can discuss is actually intermetallic compound. You will see that over here we have one vertical line. Nampak tak? Okay. At around 70 something lah. Maybe 78 or 79. So this is actually a formation of intermetallic compound of what? So this is actually a formation of epsilon lah, intermetallic compound of epsilon. Okay, so just some other things that you can I think discuss lah whenever you see any phase diagram. So for a more complicated I think phase diagram, you can see from these examples. Okay, you can see there's a lot of reaction that can occur. Okay, so all of this actually they discuss anything with regards to any horizontal line. So kita nampak ada horizontal line. Okay, so for example like this one, so we see one horizontal line, and then the face boundary is located on top. Okay, atas dia apa? Atas dia beta. Kita nampak atas dia ni beta. Bawah dia theta plus neta. So this could be the eutectoid reaction because we know one solid forms another two solid. What else? Okay, so kita nampak yang ni pula. Okay, at around 600 something. Okay, so the phase boundary is located on bottom. The top reaction is actually alpha plus beta, and at the bottom is actually theta. So this is actually peritectoid. Peritectoid. You have a mixture of two solids that form one solid. Okay, other things. Okay, at around 600 something. So you have another vertical line, horizontal line, with a phase boundary located on top, which equals to L2, L2 ke L1, campuran. Okay, and then at the bottom you have alpha plus beta. Okay, so macam tu lah. I think it's not really complicated lah to read the reaction. It's just that to memorize what types of reaction that we are talking about. Okay. Alright, so as a summary for this, I think first two parts of this chapter, we already have understand how you can identify number and types of phases present in the phase diagram. And apart from that, the composition of each phases can be easily identified using a lever, rule, or tie line, I think, formula. And the weight fractions can also be identified using this, I think, lever rules formula as well. Okay. And the microstructure of an alloy is also depends on the composition and whether or not the cooling rate allows for maintaining of equilibrium. Okay. And finally, the importance of phase diagram, phase transformation include eutectic, eutectoid, peritectic, and monotectic. So all these reaction that we have seen. Okay. So today we are also going to I think study the last part of this chapter, which is on the ternary phase diagram. So when we talk about ternary phase diagram, we understand that ternary actually means that it is actually a three component, three elements of phase diagram. Okay. The diagram of ternary phase diagram represents the equilibrium between the various phases that are formed between the three components as a function of temperature. Normally, pressure is not a variable in ternary phase diagram construction and is therefore held constant at 1 atm. Okay. So for Gibbs phase rule for three component system, is known to be as follows. So we have F is equal to C plus 2 minus P. Okay. If you have isobaric isotherm, what does it mean by isobaric system? Anyone remember for physical chemistry? What does it mean by isobaric? Siapa tahu? Okay. So isobaric is actually means that you have a constant pressure lah. Okay. Right. So for isobaric system, then F is actually equals to C, component plus 1 minus with phase. For C, component that is equal to 3, the maximum number of phases will coexist when F is equal to 0. Okay. So when phase is equal to 4, phase is equal to 4 when composition is equal to 3 and F is equal to 0. Right? And for a ternary phase diagram, it is not similar as what you have seen in the first few examples of binary phase diagram, binary eutectic, binary eutectoid, and whatsoever. For a ternary phase diagram, the phase diagram actually exists as a triangle. Dia bentuk triangle. Okay. I guess maybe if you study physical chemistry, maybe level 3 or level 2, you will see a phase diagram of maybe gas or whatsoever. It's actually in a triangular shape. So Gibbs triangle is an equilateral triangle on which the pure components are represented by each other. Okay. So examples, if you have a alloys that is formed with 3 elements. For example, stainless steel. So stainless steel you can have iron, and apart from iron you can have chromium, and apart from chromium you can also have nickel and whatsoever. Okay, so that is why you have 3 axes. You have axis actually represents the purity of the components. And the unit for each axis is actually to be noted as percent weight or atomic percentage, which in the end equivalent to the molar percentage. When you actually divide weight over atomic mass, then you get molar lah. Okay, right. So all these are actually used to determine the overall composition. For example, if you have mole fraction of A plus mole fractions of B plus mole fraction of C, in the end, it will actually equals to 1, okay, or 100%. Okay. So for example, if you have one point X at different composition, okay, so you know that the overall composition actually make up from a few percent of A, a few percent of C, and few percent of C. So all this actually can be noted or can be identified by looking at the length of each lines. And similar things, we are still looking at the the tie line. The tie line, the lever rules, in order to calculate the percentage fraction or the weight fraction of a component. For example, at point X, if you want to calculate the composition of A, atom A, then the fractions will be the distance between M with X, mx, okay, over here, over distance of MA, the overall. Okay, sebab kita nampak kat sini, kita nak cari apa? A kan? Okay, so let's say that A, so we draw a line over here. So this will be your R and this will be your S. Okay, so A is located over here. The opposite line is actually S lah. So sama, same things will apply. So you will have A is actually equals to MX or XM over the total length, which is MA. Right. How about B? So B pun sama juga. Think if you want to calculate the percentage of B, so you have R and also you have S over here. So B, the opposite line is actually S. So the distance of S is actually N and X. So B is equals to NX over the total length, and B. And finally for C, okay, C is located over here. Okay, so still the same, we name it as R and S. Okay, opposite line is S over here. So S is actually LX, okay, over the total length, LC. Okay, so this is actually how you can calculate the composition, the overall composition of point X. Okay, all right. So we have one triangle like this. I didn't show yet the phases and everything because we just want to know how we can read the value. Okay, so you have like one point over there. Determine the overall composition. So if you have time, you can actually copy this link. Okay, this is actually a simulation software. I think developed by some groups in in the University of Colorado, Department of Chemical and Biological Engineering. Okay, so what actually they have developed is basically they develop um, the how to say the simulation in order to calculate apa tu the fractions or the composition of the points. Okay, so you can actually copy and you can actually try the simulation. Okay, so for this case, how you are going to identify, and we know that for this phase diagram, we have a composition of A, B, and C, and this is actually the fractions. Okay, so it is actually reported as decimals, but you can also write it as 10, 20, 30, and whatsoever. Okay. So how to do that? So this is actually I adopt from the simulation that we I think download, or maybe you can try from the link that I give to you before. Okay. So you have this point. So how actually you want to find the mass fraction of A and mass fraction of B and C? Okay. Alright. So for A first. So kita tengok A is located on top, isn't it? Okay. So what you are going to do is first you just make a vertical line like this. Okay. Kita buat satu vertical line macam gini. And then the point is actually located here. So you just draw any lines that is actually perpendicular, okay, to the vertical line that you draw just now. And this should be like 90 degree. So how to read? So if you want to read A, okay, so we have to read it here. Okay, so this is actually represents the percentage fraction of A. So bila kita dah tarik sebelah sini, berapa value dia? Kita tarik, so the value is actually 0.4. So fractions for A is actually equals to 0.4. Okay, and how about B? Okay, saya tukar warna lain lah. Katakanlah saya pakai warna hijau sekarang ni. B. Okay, so B is located over here. So still the same. You just draw the line. Yang membahagi dua lah. The triangle. Okay. So for B, where should be the values that you read? You should read it from here. Okay. Because kita nampak B kat sini kan. B is actually 100%. So from 0.1 until 100%, this is actually the values lah. Okay. So any lines that actually intersect or perpendicular with the vertical line that you draw for B, so it should be here lah. Okay. Okay. So yang ni pun 90 degree. So what's the value? Value is still 0.4. X B is equals to 0.4. Okay. Alright. And then finally for C. C ni boleh try jugalah. Okay. I use another color. Maybe this time use purple, pink, sorry. Okay. So C dekat sebelah sini. So draw the line. Okay. And then this should be the values that you should read for C lah. So kat mana dia punya line yang you nak kena baca tu? Is actually over here. Nampak tak? Ini pun 90 degree. So what's the value? It's actually equal to 0.2. Okay. So in the end of the day, you can get the value lah, the mass fraction of apa tu? Point point kita tak bagi nama dia, point A lah for example. So we have a fraction of 0.4 of A, 0.4 of B, and 0.2 of C. If you sum these two things together, kalau kita campur dia punya value tu semua sekali, you will get the value is actually equals to 1. Kalau kita tambah semua sekali, if you sum all these three value, you will get 1 or 100%. Okay, is it clear? Ada apa-apa soalan setakat ni? Now we are going to look at a more real examples. Okay, so this one is actually a ternary phase diagram of a stainless steel at 900 degrees Celsius. Okay, so first question, find phase of A. So saya letak satu bulatan kat sini, satu point kat sini, A, which is equal to A. And two, find the mass fraction of A. Okay, mungkin kita boleh buat sama-sama lah. Alright, maybe I would like someone to answer this. Sekejap. Umira Fitri Kadariah Jasirin. Ini orang Jawa ni. Ada? Umira, ada?
Yes, doktor.
Okay, Umira. Apa khabar?
Baik.
Okay, Umira. So first, at point A, the first question, what will be the phase? Ini soalan kacang je.
Itu yang tu lah, chromium plus apa gamma, Fe, apa Ni. Itu lah.
Okay. So betul lah So kita nampak actually A is located in this blue region. I think it's easier because I put color here. So you can see this is actually the region and the phase will be chromium plus gamma Fe and I. Okay. Alright. Thank you, Mira. And then the more tricky question. So we are looking at the mass fraction. And from this phase diagram, we can see that we have chromium. Okay, we have chromium on top. We have iron on your left, and also we have nickel on your right. Okay, so all these three things need to be reported in your ternary phase diagram. Okay, so mass fraction. Okay, so kita ada Cr, we have Fe, and we have also Ni. Okay, so 3 orang akan buat benda ni. Agak. Wong Wei apa ni? Wong Wei Sheng. Wong Wei Sheng, are you there?
Yes, doctor.
Okay. Wei Sheng, can you actually identify or just maybe guess lah what will be the value for chromium? What will be the mass fraction of chromium?
I'm not sure, doctor.
Not sure. You cannot see, I mean, or it's quite small. Okay. So first rule, I think apply. We just draw one vertical line over here. Just make it half through lah. And then after that, what's next? Okay. So next, you just draw also another line that pass this line. Okay. And this should be the values that you read lah for chromium. Okay. If I read maybe from this value, you should read it from here. Okay. It should be like around 40 lah So let's say we say 40%. Okay, of chromium. Okay. What about the others? Iron pula. Okay. Tan Shi Leong. Are you there?
Yes,
Shi Leong?
doctor.
Okay. All right. So how about iron?
Something like 35.
35, 35. Okay. Can try. Okay. So still we draw another line over here. Pass through 50. And then for iron, we should read it from here. Okay. And then I think if we have a ruler, then it will be best lah. You confident? It's around 30 something? Are you confident?
15.
Yeah. Okay. So if you draw this another line over here, you will see that maybe this one is around 90 degree lah angle, and it passed through this line as well. Okay. Kena tak? Sip. Yep. So maybe around 15 lah. Let's say we say 15%. Okay. And how about nickel? Nickel. Seorang lagi, last person. Solawatul. Are you there?
Saya doktor.
Okay, so macam mana nickel? Berapa banyak pula?
Saya dapat 40.
40. Around that lah 40. So, okay. We can actually draw another line here. Oh, saya ingat tangan saya. Okay, alright. And then this would be the values for B. Kita baca kat sini. 40
Dapat 40.
40. Think sikit lah. Okay. I think it's around 40 plus lah. 40 something plus lah Dia tak, sebab dia kat sini kita nampak sini, and then this should be like 90. Tak kena lah. Tapi I think it should be like around, maybe we say just to be safe, 45 lah Okay. So this is actually the values lah. Kita nampak line tu, biru tu kat sini It goes till here. So this 45 lah Alright. Okay. So if you sum all this together, you get maybe around 100% lah. Dapat tak? Dapat kan? Okay. Right. So this is actually the importance. If you actually identify the mass fraction of each individual element, you have to make sure that the sum will be equals to 100%. So that is why I think later on you can check to the link that I gave to you just now. Okay. And just play around with the simulation. You will tarik point tu, and then you will actually, and try with this, I think, advice. You draw the line, vertical line, and then see what will be the line perpendicular, 90 degree, that opposites to it. Then you can actually read the value. So another question is, if let's say that I ask you, given that, for example, maybe 1 kilo, okay, or 100 grams of maybe stainless steel, okay, of SS. So what will be the mass fraction at point A? So if you already identify the mass fraction of this, like chromium is equal to 40%, okay, so you can actually calculate the mass fraction of the value of the weight fraction of chromium by just multiply it with 100 lah, 100 grams. So you will get like around 40 grams. And then for iron, 15 over 100 times with 100, you get 15 grams. And also for nickel, 45 over 100 multiply with 100 grams, you get 45 gram. Okay, 45 gram. Okay, so this also can be one of I think things or question that you can be asked lah during exams or whatsoever. Okay, right? So I hope it is clear. So we are going towards the end of our lecture. It's just to see a variation of ternary system. Okay, you have isomorphous system for ternary phase diagram. Okay, a system of ternary in this case that has only one solid phase. All components are totally soluble in the other components. Ternary system is therefore made up of three binaries that exhibit total solid solubility. And then the liquidous surface is a plot of the temperature above which a homogeneous liquid forms for any given overall composition. And finally, you can also have the solidus surface. It is actually a plot of the temperature below which a homogeneous solid phase forms for any given overall composition. Okay, for a normal isomorphous system for two system, kita nampak if let's say that we have binary A and B, the phase diagram is going to be like this. You see that macam ada bentuk daun kat sini. How about B and C? Kita ada B and C pula. So isomorphous juga. Bentuk dia macam ni. And C and A katakanlah macam ni. So if we combine all these three isomorphous phase diagram system, okay, it will actually produce like a three-dimensional ternary isomorphous phase diagram. So you will see that if we actually combine this, it will form like a triangle. And at the same time, this is actually the isomorphous system lah. So you have liquid plus alpha, same lah for others. Okay, and this is also another example of a ternary isomorphous system. But as I said to the previous class and whatsoever, for ternary isomorphous system, maybe we just understand the concept or even see the examples. But I guess maybe because of we are not two materials, maybe those who are studying materials engineering, metallurgy, they will use this a lot. So in chemistry, maybe we are not using it a lot. For us, maybe it's just enough to understand how you can read the ternary phase diagram and you understand what would be the basic concept in ternary phase diagram, then it will be enough. Okay, right. So I guess maybe we've come to the end of our chapter 9 for the phase diagram. I will start to post your assignments probably from today. Okay. The first assignment is basically on a phase diagram, and this assignment is actually individual assignments lah. So saya kalau boleh nak you do it individually, and then maybe I will give you around 1 week plus lah to settle the question, and then after that you can submit it through the e-learning as well. So don't worry, I guess maybe the deadline will be next week Friday lah. Okay, right? So ada soalan? Ada apa-apa yang nak ditanyakan? Anything that you would like to ask? Anything? Okay. So if there's no question, no further question, I think let me share your attendance for today. Okay. I will stay back for a couple minutes to answer any question from the floor, if any. Or if that no question, so I will join the class. Thank you very much for your kind intention. Hope to see you back next Monday, 10 a.m. And with that, thank you very much and have a good weekend to all. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, doktor.
Welcome.